Let's look at our schedule. Today's our last class talking about polynomial functions. We're going to talk about zeros some more today. Yeah. Wednesday, I'm going to give you a take-home quiz that will be due Friday. And then next week, you've got project 3 due. Okay, let's just do the preview exercises together. I have a quadratic equation. How do I solve it? Quadratic formula, yeah. And I could try to factor it, but in this case it doesn't factor, so I just got to use the quadratic formula. So the quadratic formula is x is negative b plus or minus the square root of b squared minus 4ac all over 2a. And then replace a, b, and c with the values of the coefficients on x squared x and the constant. So this is going to become negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times negative 1 all over 2 times 1. All I can hear is Jessica's voice right now. It's distracting me. Thank you. Okay. So I've got negative 4 plus or minus the square root. Negative 4 squared, what is that? 16. And then I have negative 4 times 1 times negative 1, so that's plus 20 all over 2. So this is negative 4 plus or minus the square root of 36 over 2. Negative 4 plus or minus 6 over 2. And then you just do the plus and the minus. So you do negative 4 plus 6, which is 2. 2 over 2 is 1. And then you do the minus. Negative 4 minus 6 is negative 10. Over 2 is negative 5. Square root of what? Oh, yes. Oops. That worked out too nicely. Yeah, so this should be plus 4. I let my brain go faster than my hand was writing. So this is negative 4 plus or minus root 20 over 2. Yeah. And then the square root of 20 is not a perfect square, so I can't just take the square root. I could simplify square root 20. Yeah, I can pull a 4 out. So it's going to be negative 4 plus or minus the square root of 4 times 5, which is 2 root 5. Yeah, so this is negative 4 plus or minus 2 root 5 over 2. And then you can break it into 2 fractions, negative 4 over 2 plus or minus 2 root 5 over 2, and reduce each fraction to get negative 2 plus or minus root 5. So that simplifying this, once you get to here, this is just straight the quadratic formula, right? Simplifying that is a skill that you should have picked up before today, right? But just as a little refresher, to simplify the square root of 20, you just say, are there any numbers that divide into 20 that are perfect squares? And you go, oh yeah, 4. 4 is a perfect square, and it goes into 20. So you rewrite the 20 as 4 times 5. And then you can take the square root of the 4 because that's the perfect square. So the square root of 4 becomes the 2. And then you break it into 2 fractions and simplify. All right, let's do another one. Quadratic formula again. So I get x is negative 4 plus or minus the square root of 4 squared minus 4 times a times c all over 2. So that's going to be negative 4 plus or minus the square root 16 minus 24 negative 8. Say what? It could not be easy. No, no. Yeah, so how do you take the square root of a negative again? You need an I. You can pull out an I. And then I can also pull out a 4, right? So I'm going to rewrite the square root of -8 as -4 plus or minus the square root of -1 times 4 times 2. Okay, so I rewrote -8 as -1 times 4 times 2. So the first two things I chose because I can take the square root of them. The square root of -1 is I, square root of 4 is 2, and then I have some leftover stuff. So then simplify by taking the square root of whatever you can. So this is -4 plus or minus 2I square roots of 2 over 2. And then break it into two fractions, -4 over 2 plus or minus 2I root 2 over 2, and reduce. -4 over 2 is -2. Those cancel and you get I root 2. So today you might be guessing we're going to be dealing with zeros of polynomial functions that are irrational and have square roots in them, and imaginary that have i's in them. All right, so one last thing in the preview. F of x is some number a, I don't know what a is, times x to the fourth minus 3x squared minus 4. And I'd like to know a, and the only information I have is that f of 3 is -150. So f of 3 means plug a 3 in for all your x's, right? So a, unknown, I'll leave it as an a. So this is 3 to the fourth minus 3 times 3 squared minus 4. And when I do that, when I plug a 3 in for all my x's, I'm supposed to get -150. And now, this is just an equation where the only unknown is a, and I can solve for a. So this is a times 3 to the fourth is 81. It's 27 minus 4. Anybody do that in their head? 81 minus 20 would be 61, minus 7 would be 54, minus 4 is 50. Divide both sides by 50, so you get a is -3. We'll be using that trick a lot. Everybody's got this? Okay. All right, so when you're finding the zeros of a polynomial function, what kind of numbers can you get? You can get nice rational numbers, and that's what we've been getting up until today. All of our zeros have been easy to handle numbers. Today we're going to start talking about what happens when you have irrational zeros and imaginary zeros. So here's a polynomial in completely factored form. Every factor is linear, right? So my exponents on my x's are all ones, right? So that's what I mean by linear. Every factor's exponent is a 1. So I want to find all the zeros of this polynomial and classify each one. Real, non-real, imaginary, complex, rational, or irrational. Okay, so looking at this first factor, if x plus 3 is a factor, what has to be a 0? -3. So my zeros are x equals -3. And to classify that, that is a rational number. Okay. And then that happens twice, because my next factor is also x plus 3. Right, so I might just write multiplicity 2 here, because it happens twice, instead of rewriting it all again. Okay, my next 0, if 2x minus 1 is a factor, what is my 0? Set 2x minus 1 equal to 0 and solve it. 0.5 or 1/2, yeah. And what kind of number is that? Rational, irrational, complex, rational. It's a ratio of two whole numbers, that means it's rational. Okay, x plus the square root of 2 is a factor, so what's the 0? Negative root 2. What kind of number is root 2, negative root 2? Irrational. Imaginary means it has an I in it. Yeah. And the negative is not under the square root. Yeah. I see what you're thinking there. That is irrational, not imaginary. And then my next factor, x minus root 2, means that my 0 is x equals positive root 2, which is also irrational. X minus 4 plus 5i. What's my 0? Say that again? I just couldn't hear the 4 minus 5i. Yes. What kind of number is that? Nope. It's a complex number and it has an imaginary part. So we say complex imaginary. And then my next one, if x minus 4 minus 5i is a factor, what's my 0? 4 plus 5i. And that's also complex imaginary. Good. Complex means it looks like a plus bi. Yeah. So technically, like this x equals negative 3 is a complex number because you could just say the b part is 0, right? But we typically don't because we're so used to dealing with real numbers. All right, what's the degree of this polynomial? What if you multiplied all that together, what would the highest power on x be? No, after you multiply it all together, if you're going to distribute everything to everything else. No. It's 7, yes. Well, how did you get 7? Yeah, you counted all the factors. Yeah. If you multiply all your factors together, okay, you multiply these two together, the highest power of x you're going to get is an x squared, right? And then x squared times something else will give you an x cubed. And then x cubed times another x is x to the 4th, times another x, x to the 5th, times another x, x to the 6th, times another x, x to the 7th. So the degree would be 7. And then how many linear factors are there? 7. You just count them all up. 7. And how many zeros does it have if we count repeated zeros? 7, yeah, because the negative 3 is 1, 2, 3, 4, 5, 6, 7. Okay. And this is not a coincidence. If you count multiplicities as separate zeros, and you count complex imaginary numbers, then you always have exactly the same number of linear factors as zeros as the degree of the polynomial. All right, so here's a cubic polynomial. We're going to find the exact values, meaning no rounding anything. If there are radicals, we're just going to leave them in there. Exact values of all the zeros of this polynomial, and we're going to write it in completely factored form. So I'm doing two things, finding the zeros and factoring it. So I have a picture from my graphing calculator here that shows we have one nice integer valued 0 at x equals 2. Okay, so I have 1, 0 at x equals 2, which means what do I have as a factor? X minus 2. Great. Okay, so once I know one factor, how could I get another factor? Division, yeah. So I'm going to do x minus 2 divided into my cubic polynomial. All right, so here's a good opportunity for us to review from last class, polynomial long division. So you start by just looking at the leading terms here, and you ask yourself, what do I multiply x by to make x cubed? X squared, so that goes up here. X squared times x is x cubed. X squared times negative 2 is negative 2x squared, and I subtract. Being careful to distribute that negative sign. So x cubed minus x cubed is 0. X squared minus negative 2x squared is 3x squared. Bring down the minus 5x and start again. What would I multiply x by to make 3x squared? 3x. So then multiply 3x times x minus 2. You have to distribute it to both terms. So 3x times x is 3x squared. 3x times negative 2 is negative 6x. And subtract. 3x squared minus 3x squared is 0. Negative 5x minus negative 6x is x. Bring down the 2, the minus 2. And x minus 2 goes into x minus 2 one time. And subtract, and I get a remainder of 0. Oh, and I just did all that work that was supposed to be in part C. That's okay. So now that once I had a 0, x equals 2, my factor was x minus 2, and then divide. See above. Okay, so now I'm going to write my cubic as the product of two factors. Okay, I now know that f of x could be equal to x minus 2, my first factor, that I knew because I knew a 0, times x squared plus 3x plus 1, the quotient. All right, so now we got to remember our goal. We're trying to find all the zeros and put it in completely factored form. Okay. So to find zeros in general, you set your function equal to 0 and solve it. So I would set f of x equal to 0, x minus 2 times x squared plus 3x plus 1 equals 0. I have two things being multiplied together. The answer is 0. How do I proceed? At least one of them is 0. So either x minus 2 is 0, which gives me x equals 2, and I already knew about that 0. Or, right, x squared plus 3x plus 1 is 0. And how do I solve that? So yeah, what we reviewed right before we started the demo, the quadratic formula. Right, so in this case, x equals negative 3 plus or minus the square root of b squared, which is 9, minus 4 times a times c all over 2a. So that's negative 3 plus or minus the square root of 5 over 2. And I'm just going to take a second to remind myself that this is two separate zeros. This is negative 3 plus root 5 over 2, and negative 3 minus, negative 3 minus root 5 over 2. You can just circle the plus or minus one, but I just wanted to sort of have that clear in my mind. That's two separate zeros. So I now have 3 zeros. It was a cubic, and so there should be 3 total zeros. Okay, so my 3 zeros are at x equals 2, x equals negative 3 plus root 5 over 2, and x equals -3 minus root 5 over 2. So I've got 3 zeros, which means I should have 3 factors, and I can write it in completely factored form. X minus 2, x minus -3 plus root 5 over 2, and x minus -3 minus root 5 over 2. What's the degree of that polynomial? 3, right? When it's written all out, multiplied out, it had degree 3. And it has 3 linear factors that I just wrote, right? 1, 2, 3, and it's got 3 zeros. Okay, so a couple of conclusions. If a polynomial has degree n, then if we count multiple roots separately, the equation has n zeros, real and non-real together. It's exactly n zeros. An nth degree polynomial can always be written as the product of some non-zero constant times n linear factors. And each factor looks like x minus c, where c is one of your zeros. And a plus bi, if a plus bi is a 0, then a minus bi is also a 0. Right? So that will always happen because of the quadratic formula with the plus or minus. So a plus bi and a minus bi always show up together as zeros. Same thing with irrational zeros, again, because of the quadratic formula with the plus or minus in it. So if 1 plus root 2 is a 0, then 1 minus root 2 is a 0. All right, so one more example we'll do together. I want to find a 3rd degree polynomial, has real coefficients, and it has -3 and I as zeros. And f of 1 equals 8. So I want to put it in factored form and standard polynomial form. So it's 3rd degree, right? 3rd degree. So how many factors does it have? 3. How many zeros does it have? 3. Okay, how many zeros did they give me? 2. Okay, so I need 3 if I want to write this in factored form. So there's another one that's implicitly given here. They didn't explicitly write it down, but we know it's there. Think of I as 0 plus I. What else? 0 minus I has to be in there too. So negative I is a 0. Right? So also negative I, right? Because complex zeros always occur in conjugate pairs. A plus bi and a minus bi always occur together. So if I is a 0, so is negative I. Okay, so I've got some unknown leading coefficient a, and then my factors are x plus 3, because -3 was a 0, so x plus 3 has to be a factor. X minus I, that's because I is a 0, and x plus I, because negative I is a 0. All right, let's multiply it out. So this is a. I'm going to save the x plus 3 for a minute. And I want to FOIL x minus I, x plus I. So I get x squared plus ix minus ix. So what happens when you have 2 terms that are the same, but one's positive, one's negative? They cancel and make 0. Yeah. So I have plus ix minus ix, they cancel and make 0. So the outer and inner terms here just cancel. And then I have minus I squared. Yes, yeah, if you think back several classes, I squared is actually the number -1. So this is minus -1. So this is a times x plus 3 times x squared minus -1, which is plus 1. All right, now let's FOIL x plus 3 times x squared plus 1, or the lobster claw or the box, however you learned how to think of that. So this becomes a times x squared is x cubed. And then my outer term is x. And my inner term is 3x squared and plus 3. All right, I'm almost done. How do I figure out what a is? Yeah, use the last piece of information I was given here. We did an example like that in the preview. If f of 1 equals 8, that means that if I put in 1s for all my x's, I should get 8 as my answer, and then a is the only thing I don't know. So that's 1 plus 3 is 4, plus 1 is 5, plus 3 is 8. So 8a equals 8, so a is 1. So to finish up, I just have to write this all out again, where I give my answer in both factored form and the multiplied out form. So f of x in factored form looks like this. And I just have to replace the a with the value I know it is. In this case is 1. So I'm just going to do x plus 3, x minus I, x plus I. And you can write the 1 there or not. Multiplying by 1 doesn't do anything. So that's my factored form. In my multiplied out form, I was almost there at this point, right? All I have to do is replace my a with a 1 and distribute it. So that's, if I replace the a with a 1 and distribute, I just get x cubed plus 3x squared plus x plus 3. Okay, so just a quick note about your homework for class 29. The directions say, quote, use the rational zero theorem, Descartes' rule of signs, and possibly the graph of the polynomial function shown by a graphing utility as an aid in obtaining the first zero. I did not teach you the rational zero theorem or Descartes' rule of signs, right? So I don't want you to use those to find the first zero. Just use a graph, either GeoGebra or a graphing calculator, to find the first zero. Just like we did in class, just like we did with number 2 here. Look at a graph and say, oh, it crosses the x-axis at one nice point. Use that as your starting point to get 1, 0, and thus one factor. And then you use polynomial long division after that to find the remaining factors / zeros. Okay, so you can start with some practice right now. If anybody needs a graphing calculator, I don't think you do. I think I gave you pictures for the class activities. Yeah.